All right, everyone. Welcome to another episode of the TWiML AI podcast. I am your host, Sam Charrington. Today, I'm joined by Anna Ivanova. Anna is a postdoctoral researcher at MIT Quest for Intelligence. Before we get into today's conversation, be sure to take a moment to head over to Apple Podcasts or your listening platform of choice. And if you enjoy the show, please leave us a 5-star rating and review. Anna, welcome to the podcast.
Thank you so much for inviting me.
I'm really looking forward to digging into our conversation. We're going to be talking about some of your research into kind of the intersection of large language models, ChatGPT, intelligence, really interesting topics. Before we do that, I'd love to have you share a little bit about your background and how you came to work in the field. And please be sure to touch on what is MIT Quest for Intelligence?
Yeah, so I'm a newcomer to the field. AI is not my area. I am coming from neuroscience. I just defended my PhD last summer on the topic of the relationship between language and thought in humans. And I addressed this question using neuroimaging. So, looking at brain activity in people doing different kinds of tasks using functional MRI. So they lie in this giant magnet, this giant tube. We can see activity in their different brain regions as they're doing different tasks.
Mhm.
Now I'm using my training in neuroscience and in cognitive science to turn to large language models to see, do they behave in human like ways? Do their internals resemble the internals of human brains? Right? So, to what extent do large language models do language in a similar way to humans?
Essentially trying to unpack this idea or question of does ChatGPT think, right?
ChatGPT is so new that we know very little, but we have a lot of information on earlier models, right? The GPT line that was a precursor to ChatGPT, and in general, large transformer models trained on gigantic amounts of text. And so we might not know all the things yet about ChatGPT, but we can say quite a bit about this general class of models. And you also asked about MIT Quest for Intelligence. MIT Quest for Intelligence is an initiative that got launched a few years ago that aims to bring together scientists and engineers. Because MIT, on one hand, has amazing research facilities and many people like me with a science background. But of course, we also have a lot of engineers that come up with new tools and inventions. And so this is an attempt to bring together scientists and engineers in academia and also in industry. The Quest has a bunch of industry partners in order to bring these two fields together. And so essentially, it's just an MIT internal initiative that isn't tied to a particular department. I guess technically its home is MIT's new College of Computing. But in general, there are many professors from many different places that are working on this quest.
Awesome, awesome. So maybe we can jump in and have you share a little bit about how you conduct your research. You can't take a large language model and ask it to lay down on a MRI machine. So very different setting than what you've done with humans.
Yeah, so there are multiple approaches, and the easiest one, perhaps, is to look at this model's behavior, right? Just as in humans, we can ask humans to do a bunch of different tasks, answer questions, see how well they respond, how accurate, whether the responses are consistent with each other. We can do the same thing with models. So, if we want to measure a particular ability in a model, if we come up with a way to ask our questions in a way that the model understands, we can then evaluate its behavior. And these models are generative text models, so they're very good at generating sentences. GPT models generate them word by word. And so, what we can do is we can, for example, see how likely is a particular sentence in response to a general prompt. Or, for example, you can look at sentences like, yesterday I went to the beach versus yesterday I go to the beach. One of them is grammatical, one of them is ungrammatical. We know that yesterday should be accompanied by a verb in the past tense, so went and not go. And so we can just measure how likely is a model to generate one sentence versus another. And so we can see systematically, do these models perform grammatical outputs over ungrammatical outputs.
And uh, a big part of your work, or at least I should refer specifically to a recent work that you're a co-author on, dissociating language and thought in large language models, is just that, trying to pick apart with these models, what constitutes just a functional kind of use of language versus, what is, I guess, higher level kind of uh, reasoning or thought. How do you think about this distinction that you're trying to get at with your research?
So there has been a lot of debate in the field about how useful these large language models are, especially before ChatGPT came out, and now everybody's crazy about it. With these earlier models, right, where um, they were clearly doing something very impressive. They were generating texts. They were already generating texts that were hard to distinguish from human generated texts, but it wasn't super clear what they're doing, how much of language did they actually learn, do they understand language. And so there has been a big debate in the field, with some people saying clearly this is a step to AGI, we just need to keep scaling up and these models will bring us all the way to general intelligence, and other people saying no, these models are useless, all they do is copy and paste pieces of text and kind of stitch them together, but this is nothing like intelligence. So there were these very, very radical positions in the field. And so what we've tried to do is we've tried to add more nuance to this debate. We're saying, look, there are different kinds of capabilities that we need to be paying attention to. On one hand, we have what we call formal linguistic competence, and that's just the ability to use a language. So if we're talking about English, right? Does the model know grammatical rules of English? Does it know which words tend to go together, right? So did it learn the rules and patterns and regularities of the English language? On the other hand, we have functional linguistic competence, and that's the ability to apply your knowledge of a language to actually do things in the world, to extract the meaning from a sentence, to generate sentences that refer to real things in the world. When we are talking, the first thing that happens is we have an intent. We want to communicate something. We want our listeners to receive some kind of information. Maybe I want to, cause you to think differently or cause you to do something, right? There is this intent that's essential to us talking to one another. But the models don't have that. The models, they just generate utterances, they put words together based on what's plausible, what sounds like right, what mimics the patterns that they've encountered in their training data, right? And so this intent is one of the aspects of what we call functional competence, the ability to use language to do things in the world. And these models don't have that. And so, on one hand, we have models which we've never had before, where they are really, really good at generating natural sounding sentences. This is a huge breakthrough, and we need to acknowledge that. But on the other hand, we cannot yet equate them with general intelligence. They are very far behind on many aspects of functional linguistic competence, so they don't understand and use language in the way that humans do, at least not yet.
Hmm. Hmm. You drew a parallel between, or maybe an equivalence, not, although not strongly, between functional linguistic competence and AGI. Can you elaborate a little bit on that? I can envision a model demonstrating some degree of functional linguistic competence, yet still not, qualifying by what most reasonable people might call AGI.
So some of it, I think, depends on your definition of AGI, right? Does it
Fair.
reflect all of human-like intelligence, or are we referring to specific aspects of it? There are very interesting. Since the paper came out, we've had a couple of interesting discussions, where we'll probably want to highlight in future iterations of the manuscript that intelligence also encompasses domains that are hard to access through language. For example, our ability to navigate, or motor intelligence, catching a ball. These are things that are very hard to describe in words because these are continuous values, usually not discrete. But we can use that. We have a lot of this sophisticated types of intelligence. And whether or not you want to call them AGI, right, that's up to you, right? Is the ability to um, exhibit this kind of spatial motor intelligence. Is that AGI or not? But as insofar as we're talking about functional linguistic competence, we're talking about domains of knowledge that are not specific to language. For example, we can access the concept of a cat through a word cat in whatever languages you know, but also through a picture of a cat, through a sound like meow, right? Like they can all trigger the same concept, but it doesn't it's not linguistic per se. So a lot of our conceptual information, a lot of our world knowledge resides outside of language proper, even though a lot of what we learn about the world we do learn through language. And so that's a more general kind of functional competence, our intelligence, our ability to know and reason about the world, but it's not specifically tied to language, at least not in the human brain. So we have examples where people get a stroke, their language regions get knocked out, they don't function anymore, and so people get aphasia, which is a disorder of language, either comprehension or production or both. And so these people might have trouble speaking and expressing their thoughts, but their thinking process remains intact. And so this is a very clear example of this difference between language and thought that we think the models would also exhibit.
So you've got kind of formal linguistic competence, functional linguistic competence, and functional linguistic competence. You you kind of equate to some degree AGI. Um, when I think about like what your initial example of functional linguistic competence, making arguments, things like that, ChatGPT does a decent job at that. You can say, make an argument in support of XYZ, give me 3 points and, support them. It'll even make up URLs for those points. Maybe go a little bit deeper into how you define functional linguistic competence, so we can understand that the distinction there.
Yeah, so there are different domains, right? So there is the ability to reason, the ability to do math, which might or might not be related to formal reasoning skills. There is world knowledge. There is this global modeling of a situation and tracking down what happens to whom when, which is very important for understanding narratives, movies, stories. And there is social competence and intent, which I talked about earlier. And so we should be able to evaluate each of these capabilities separately in these large models, in addition to evaluating formal competence. So we're not saying that these models will never reach functional linguistic competence. We're saying that these are distinct capabilities that in the human brain are supported by distinct systems. So we don't have a reason to think that they will all develop simultaneously to the same degree, that we need to be able to conduct specific testing each one of these capabilities. And whether or not ChatGPT can reason is a good question because we don't know what went into its training data, right? We don't know how much of what it knows it was just given direct access to during learning. And so usually what these models struggle with is generalization, right? They trained on one kind of arguments, they need to generalize to another type of arguments. To be fair, ChatGPT is better than most models before at modeling styles, right? So it knows what a syllogism would look like, right? Like what the logical chain would need to look like to be convincing. And it does seem to be fairly good at paraphrasing, right? Even if it received information in one form, it can then rephrase it in a different form. So that's a huge advance. But can it generate novel arguments rather than repackage existing ones? I think that's still a big question.
In your work, have you it was part of the work, kind of, you've identified these areas of functional competence. Have you mapped those to existing benchmarks and tried to identify where the gaps are? Like, do we have benchmarks for all of these things, and we just need to throw ChatGPT or GPTX against them, or are there areas where we need wholly new benchmarks and they haven't been quite figured out yet?
Yeah, that's a great question. So our paper at its core is a review paper, right? We draw this distinction between formal and functional competence. We identify different domains within functional competence, and then we review available literature trying to see how good these models are. And so what we think we see is that the current models up to ChatGPT are much better at formal linguistic competence compared to functional linguistic competence. So there is this disconnect. But you're right in saying that for a lot of domains, the benchmarks don't clearly identify the domain that we might care about. They might conflate, for example, formal and functional competence. Of course, these models are just so good at memorizing specific patterns of words that we really need to keep that in mind when evaluating them, because if they learn that certain words tend to go together, they might often give you the right answer without necessarily figuring out the underlying logic. And so that's a very common issue that keeps coming up again and again when trying to figure out what these models know and don't know. And actually, one of the projects I'm currently working on is trying to develop a benchmark for testing world knowledge in large language models. So that's one of the big things I'm working on now. So what we've done is we've identified a range of fundamental concepts that humans use when they try to think about the world, the fundamental building blocks, essentially. So, a lot of concepts from intuitive physics, right? Like mass and size and physical relations, like in and on and around, and intuitive psychology, so knowing what an agent is and what a goal is and what helping is and stuff like that. And so now we're developing a benchmark that will try to systematically probe all of these concepts in large language models.
There's an argument that some researchers hold that for a lot of the concepts that you identified in this context of world knowledge, language alone is insufficient. Like it needs to be grounded by, some other type of perception, vision, etc. What's your take on that as someone coming from the neuroscience and cognitive science side of things?
So, on one hand, language tells us a lot about the world. So, first of all, explicitly, right, I can tell you facts about the world. Um, Most ones are white, right? And so that tells you something about the physical world. Um, and you know color properties of certain animals. And in addition to that, in addition to explicit knowledge, a lot of knowledge is conveyed implicitly through patterns of words occurring together, right? So I don't know, dogs tend to bark, cats tend to meow, and a lot of the stuff we can learn just from listening to a lot of sentences or reading them and kind of figuring out what concepts go together. And the fundamental example of that is blind people who learn a lot of visual concepts even if they were born without sight. So many blind people will be able to tell you that red and orange are more similar to each other than red and blue as colors, even though they've never experienced that. They just know that from language, from being exposed to language. And many will also know the difference between glance and stare, for example, right? Very visual verbs, but they know the differences in meaning just from language input. And so language does have a lot of information even about physical things in the world. So you don't always need access to the physical reality. Language does reflect a lot of that. But on the other hand, linguistic information is biased, and this phenomenon is also known as reporter bias because we tend to talk about things that are unusual or interesting. So, language, we don't just describe everything that we see, we talk about things that are unusual. I'm saying, oh, like this banana is yellow. It's like, no, we know that most bananas are yellow. It's not very interesting. But if this banana is purple, I'm much more likely to comment on that because it's less common to see a purple banana. And so, the texts that these models are trained on, they contain a lot more unusual information compared to what things are like in real world. And so these models for the longest time had trouble learning, for example, that wheels are round because you would just never talk about wheels being round. Like everybody already knows that. So a lot of common sense knowledge is not reflected in text, at least not in natural text that you would find on the internet.
Do we have a way to solve that, this reporter bias with large language models? Is it, simply, a scale? approach thus far? Well, if we collect, even more documents, someone's going to be talking about round wheels and yellow bananas. Or are there other techniques that you've come across for imparting this kind of common sense, right?
Yeah. Well, scaling up will not get rid of the bias. It will give you more information, but the bias will still remain. And so maybe there are some techniques that can be employed to correct the bias, to even out those distributions that we see in text. Um, of course, a way to do it, mm, you know, most efficiently and most appropriately would be to try and build a system that acts like a human, that is able to infer missing information even though there is reporter bias. You can fill in the gaps, and that is closest to the aspect of functional competence that we call situation modeling. When we receive information through language or otherwise, we incorporate it into our overall model of what's happening in the world, right? So right now, I know I'm on a podcast, I'm talking to you, we are talking about language models and functional competence, and all of that, like I don't necessarily have in my head as linguistic information, right? It's a much more abstract conceptual schema of entities and relations and what's going on. And then we hook linguistic information onto that schema and keep updating it as we go along. And so then you can, it's automatically retrieve the fact that wheels are round if we're talking about wheels, and you don't need language to help you remember that over and over and over again. So you have this latent knowledge because you have this overall model of the situation, but also of the properties of various concepts that you encounter in the world. How do we get to that with models? I have no idea. I'm not an engineer, but I think this is roughly what these models would need to have in order to be much more efficient and much more powerful when reasoning about the world.
Meaning, or paraphrasing, you don't anticipate that a single kind of end-to-end trained LLM, along the lines of the way we train them now, collect a lot of data and run through a training process, will be able to address all the various aspects of functional competence. It's more like some kind of modular system.
Yeah, so we argue in the paper that based on what we know about the human brain, which has this highly specialized components for different kinds of cognitive processes, a model that uses language in a human like way would also need to be modular. But we do make a distinction. We don't try to say that, well, look, you have to build different modules in advance and then put them together, kind of like, classical old school AI architectures. We try to be more agnostic. We say that the system can be end to end. And maybe this modularity can emerge, maybe it can be induced either through having multiple objective functions to train the model on, or maybe by giving it some kind of curated data, or maybe by building the architecture such that this modularity can easily emerge on its own, or all of the above, right? So we don't have to build in the components in advance. Maybe that we can induce them, but we do need to keep in mind this distinction between different capabilities and be able to evaluate them separately. And then if we find gaps in some of them, we want to be able to selectively boost one ability or another.
In the paper, are you able to draw a direct line between the missing aspects of functional competence in current LLMs and the kinds of failure modes that we see from them, or limitations, or what they're just not good at now?
Yeah, so I think these models are still not great at reasoning and math, right? So I think just a couple of days ago, OpenAI announced that they um, enhanced ChatGPT's math capabilities. And then, of course, that same day, people on Twitter went ahead and broke them and said, like 5 people entered and me, and then two left. How many remained? And like on those simple word problems, ChatGPT just fails. So it still cannot do math. And, we argue that's because it's just a fundamentally different capability. It will, whatever patterns it learned from texts that are related to math, it will be able to reproduce. but it doesn't. It's having a hard time going from text to numbers, keeping track of those numbers, especially if it involves more than one operation. I think that's where it starts to struggle.
Yeah, yeah. And what about for some of the some of the other aspects of functional competence, situation modeling, for example?
Yeah, situation modeling is interesting because what's happening is that these models are able to, like, to some extent hack this problem, uh, because they keep increasing their context window, and we actually don't know what the context window is for ChatGPT, right? How many tokens can it attend to at the same time? It looks like it's just substantially more than earlier models. And so now essentially, instead of keep building this global model, it can get by just being able to pay attention to a lot of specific tokens from its past. And so it's fine, but then what do you do if you wanted to remember information from a previous conversation? Right? If you're trying to summarize a book rather than a chapter, like what if the input goes beyond your context window? Like at some point, you're going to run out of space, right? In this context window, which like in humans is short-term working memory, right? At some point, you need to switch to a more abstract representation, and there is a little bit of work showing that maybe these models can track situation modeling aspects to some extent, but I think fundamentally this capacity is still lacking.
Hmm. One of the areas that we see as a limitation with ChatGPT is temporal aspects. This happened before that, or it'll recount historical facts in the wrong order, that kind of thing. Um, that doesn't necessarily, at surface level, easily fit into a formal world situation or communicative intent. Where does that is that um, a composite of multiple areas of functional competence, or is it just a sub point under situation or something?
Yeah, that's a good question. I think it's closest to situation modeling, right? The ability to organize events in a sequence. So that's very similar to keeping track of a narrative in a book, right? You want to know what happens first, then next, but you also want to be able to jump between them. And we know that in humans, this ability to keep track of events and event sequences is a fundamental human ability. It's really important. It's really important for when we perceive events, when we memorize them, when we remember past memories, right? It's just this really fundamental capacity. And it's really not about language because we do the same thing when we're watching a movie or trying to recall a movie.
But you don't think of watching a movie as a linguistic experience?
No, I don't. Um, and we can get into this whole thing of differences in the style of thought, which is my favorite topic at parties. So you come up to a group of people and you ask, well, what percent of the time do you tend to think in words? And some people say like 90%. I talk to myself all the time. I hold those rich inner dialogues. I argue with myself. I plan out my conversations with others. And other people are like, what are you talking about? If they know more than one language and you ask them which language do you think in, they ask, what do you mean think in a language? So some people have no experience of inner voice whatsoever. And so there are just huge individual differences in how people perceive their own thinking, how verbal it is. And I'm sure it colors their perception of large language models, the relationship between language and thought, right? Because we kind of assume that everybody thinks in the same way as us, or at least, the same degree of verbalness. And then it turns out that no, we all have very different thinking styles. And it's fascinating because it's something that, you know, is so obvious on one hand, but there has been very little formal work, formal research on it.
Are they differences in perception, or are they differences in kind of fundamental mechanism? Maybe fundamental mechanism is too strong, but something more functional. Like I'm thinking, uh some one person might think that 50 degrees is comfortable, and to someone else 50 degrees is cold. It's just a perception or preference, but it's the temperature is the same. Is the same thing happening in the brain for the person who thinks that they are thinking in words and language all the time, and the other person but somehow they just perceive it differently? Or are their brains slightly different in some functional way?
We don't know. I'd love to find out. I think it's a fascinating question. We know we're starting to learn a little bit about the related phenomenon where we now know that some people just don't have visual imagery. It's called aphantasia. So some people can imagine rich scenes in their memory, some can imagine something, but it's kind of vague, and some just don't have visual imagery whatsoever. And there is now a little bit of work trying to see, does it affect their cognition, right? Like, do they just are they just not aware of their imagery, or does it fundamentally change the way they perceive reality and think about the world? And it looks like there are some differences. For example, they might not remember certain aspects of a scene, or they don't remember it in the same way as people with rich imagery. Like, they'll remember where something is, but not necessarily the details of visual appearance. But this is still very early days, so there is a lot more to find out there.
Yeah, it's super interesting. It makes me think a little bit about just differences between my wife and I. Like, she, if you say, you know, something like she has a very clear visual picture of that, whereas to me it's just words. And I'll play around with, and say crazy things because the sounds of words are interesting to me, and to her it's just gibberish because there's no visual associated with it.
That's funny. And to
And
some
yet
people, it's neither, right? So to some people, it's neither visual nor verbal. It's more abstract.
abstract in a way that you could characterize, or just completely abstract.
That's what they say, right? That's self-report, right? And so what is it? Do we all ultimately get to this abstract representation, but tend to code it in visual or verbal? There are just so many exciting questions there.
Yeah, yeah, interesting. So, with all of the exciting open questions on the human side of this question and these issues, like, what prompted you to jump into the AI side of this?
It's twofold. One, I think AI models are taking over the world, and it's really important to be able to know precisely what they can and cannot do so that we can use them responsibly. So I think, in terms of their impact on society, it really cannot be underestimated. And so here we see that clearly we can use tools from cognitive science and some of the frameworks that we've used to think about the relationship between language and thought, and apply those same frameworks to large language models. And I think there's been a lot of interesting discussion that's already been generated. People seem to think that it's interesting and relevant. So I'm really excited at this relationship between cognitive science and AI. And on the other hand, these language models are also a tool for cognitive science to learn more about language and about human cognition. For example, um, we know, as we talked about earlier, that humans can learn a lot about the world from language, right? So just patterns of word co-occurrences or explicit facts that we state through language. A lot of this information, even if statistical, it mirrors what we know about the world. And so the question is, do humans use this information? Do we use this purely verbal mode of thinking to solve certain tasks? Right. So um, there is this famous system one, system two distinction by Dan Kahneman that he made in his book Thinking Fast and Slow, where the logic is that you use your like fast system one thinking to make rapid intuitive decisions and heuristic based thinking, but then system two is the slow deliberate thinking that's much more similar to kind of rationed reasoning. And um, do we use our linguistic information to make those rapid system one judgments for certain tasks? And so we can get at that question by trying to see, well, do language model like what can language models do? Do language models solve certain kinds of math problems if we see them often enough, right? The multiplication table, they memorize it, maybe they can just like go and use it very easily. And so that kind of, by knowing what's possible to do with language input alone, it tells us something about what humans might be doing with language alone. So that's the direction I'm excited to pursue in my research going forward.
And are there, to date, kind of formal examples of, hey, we learned this uh, from language models, or we observed something with language models, we theorized it about humans, and we validated some new relationship or construct or function?
There has been a long debate. So, neural networks, connectionist models, really emerged in cognitive science and psycholinguistics back in like late 20th century, and they were applied to this question of whether or not you can learn. Um, Grammar, you can learn language from input alone. There were these huge debates that are really classical today about can you learn the past tense of of a verb simply by observing a bunch of verbs in present and past form, right? Just from linguistic co-occurrences in the input. Um, and I think the answer was that you can, and especially with models today, even though they require this ginormous amount of data that's way more than any human will ever receive in their lifetime, they show that it's possible to learn language, much of formal language competence, just by paying attention to linguistic input and the co-occurrences in the input. And so it kind of goes against some of the arguments stating that our linguistic knowledge must be innate. The question is not fully resolved there. Clearly, we have some biases that make it easier for us to learn language, but I think these models are pushing the boundary on what's possible to learn just from input.
In thinking about kind of this broader context of applying tools from cognitive science to AI, uh, the model that you presented in this paper, formal competence, functional competence, and the different sub aspects of competence, was that an existing model or framework in cognitive science that you then kind of map to LLMs, or is it more about kind of a way of just dissecting what thought is or cognition and applying that broad idea to LLMs?
It's grounded to a large extent in what we know about the human mind and brain. The idea to separate out formal linguistic competence comes to a large extent from the fact that we humans have a network in our brain that's specialized for language. And it's not just about reading, it's not just about speech, right? So it cares about both. It cares about both language comprehension and production. It responds to all the languages that you might know, so not just one language. And it just really seems to be a module that is responsible for language processing. And so we ask, well, which of these capabilities do large language models exhibit? And it turns out that they exhibit a lot of them, right? The ability to get to the meanings of words, put words together, syntax, all of what we call formal competence. But then we know that there are other parts of the brain and other brain networks that do other things, that are responsible for social cognition, for logic and math and reasoning, for situation modeling. And so, yeah, a lot of the distinctions we draw in the paper are based on what we know about functional specialization of the human brain.
So talk a little bit about some of the like what's next in your research, and what are you excited about in kind of the intersection of these two fields?
So one is building better benchmarks. So this cognitively informed benchmark of world knowledge is something I'm really excited about. So hopefully you'll be hearing more sometime in the coming weeks or months. And this comparative comparing the behavior of humans and large language models, I think will yield a lot of insights both about AI systems and about humans.
Do you have a sense for how you might go about that that comparison?
A lot of this we can get by with just behavior by asking humans to do a task and then asking machines to do the same tasks, and then seeing in which tasks are humans better and which tasks are machines better, right? How well do humans generalize? How well do machines generalize? Do they make the same type of errors, or do their errors differ in some systematic way? How common sense knowledge shows itself in humans versus machines, how biased humans are compared to machines and vice versa, right? You can ask so many questions, and because these machines already generate text output, they have a way to communicate their knowledge to us. So that's the easiest way, and I think the most intuitive to grasp. But there is another line of work that's very exciting that actually looks at the internals of these models and tries to compare them to what is happening in the human brain, in particular in the language network. And so what it turns out that you can map activations in the human brain to the embeddings, the vectors that you get from large language models. And so by doing that, you can actually predict brain responses to completely new sentences that the model that we haven't seen before, that we haven't recorded before. And so it looks like the correspondence between these models and humans is actually quite substantial, to the extent that you can map between the brain and the particular layer of a neural net. And so that's also an exciting tool, both to figure out similarities and differences between humans and language models, but also to learn more about the human brain. A cool paper came out just recently that says, look, if we build these models that take a sentence representation from a large language model and then predict what the human brain activity would be in response to that sentence, essentially we can get rid of a lot of experiments. We can just run them all in the cloud. All we need to do is to run our model and predict what the brain response would be to this kind of sentences or this kind of word. And so essentially, we can move neuroscience to the cloud, making it much more accessible and enabling people all over the world to run neuroscience experiments without needing an actual MRI scanner, if the model is good enough, which I think they're actually getting to be quite good now.
Yeah, just thinking about that, it's both this idea that you can create some embedding space and that maps somehow to the brain is both mind blowing, but also kind of intuitive. Like the embedding spaces mapping context, or concepts, and those concepts, should have the same distance between them, whether, it's some mathematical vector space or, some biological, space. But the fact that that works is kind of crazy, also.
It's really crazy. And of course, you can compute sentence similarity on many different levels, right? Like on the kind of surface level features, the length of the sentence, the sounds of the sentence, how frequent the words are, or based on meaning and semantics, or everything, right? And so the fact that these similarities, yeah, yeah, but like it's not at all obvious that you would be able to get that from either language models or from brains. So the fact that there is some degree of alignment, I think, is pretty cool.
The other thing that you said that jumped out at me was I forget the specifics, but we were talking about comparison and some future opportunities there, and testing uh, areas where the human generalizes and the machine generalizes. And I think we this idea of AGI kind of holds up the human as this infinitely generalizable biological machine. And it's probably much more common in cognitive science than in the AI side of things, to think about the areas where the human doesn't generalize well. And if you think about it, like, there are lots of areas where we don't generalize well. um, any thoughts on that?
I have a big pet peeve about ML papers that say that this is what the human behavior is, but then not actually running studies on humans. And so they compare model performance with some like abstract random ideal that they think should be achievable. Um, but then like I really think it is important to compare model behavior with human behavior, maybe not for all applications, and sometimes you do want this idealized picture rather than real life humans, but I do think it's important, that so we need more actual data from actual humans. But then of course, yeah, do we want these models to surpass humans? If so, what are the standards? So it is important to be very clear about what it is that you're trying to achieve. What is AGI? What do we want from AGI? Do we want AGI at all? Like, I'm not fully sold on that idea either. Um, Language is really interesting though, because like, what does it mean to be better than humans at language? Sure, maybe you will make fewer speech errors, right? Like, you will not have to correct yourself as much, But usually, when we say we want a model that's good at language, it means a model that uses language like humans, right? That's really what we want. And so, trying to build a model that uses some kind of ideal version of a language in this perfect way, like it's not going to be useful. We want a model that uses language like us. So I think language is this interesting case where we don't want a superhuman model. We want a human level model.
Do you have a cognitive science influence take on why ChatGPT has been so captivating for people?
Yeah, I think why it's so captivating, that question has many answers, right? So on one hand, um, it's free and easy to interact with, and so it's easy for a person who's not technical to play around with it, right? It's just like a cool new toy. And it's trained to answer questions, so it's a direct way to interact with it. This question answer framework is very engaging, and so that's what the reinforcement learning component was very effective at, right? Training this model to produce this like paragraph length, somewhat mostly informative answers to questions. And I think that's just like a very natural way for humans to interact with something in this question answer format. Um, but then there is this issue where when we interact with someone or something and they say a sentence or write a sentence, we automatically engage all of our mental machinery thinking, why did this person say this? What did they have in mind? What did they mean? What did they not mean? We automatically come up with this image of an agent behind the person, of all of this. Like, we build a situation model. That's exactly what we do, right? We build a model of the entity we're interacting with, what they're saying, what they mean. We use our common sense knowledge to fill in all those gaps. The problem is our model fails because we used to interacting with other humans, but then we try to transfer that same thing onto machines. And so what happens is that we then think, oh, ChatGPT said I'm sad, therefore it must be feeling sad. We assume that it feels something simply because it used the word sad. And so that's where our assumptions break. And I think that's exactly why many people can be tricked into thinking that these models can think, can feel, in extreme cases, be sentient or conscious, right? It doesn't mean that these models can never think or feel or be conscious, but we cannot use their words to make those kinds of inferences because we just fill in the gaps for them.
Mm-hmm. Hmm. Awesome. Awesome. Well, Anna, thanks so much for joining us and sharing a bit about your research. Very, very cool conversation and work.
Yeah, well, thank you so much for inviting me. And yeah, I'm really excited about this relationship between cognitive science and AI, and I hope you are too.
Awesome. Thank you.